Hey guys, welcome to chapter 6, part 2. So as promised, I said we were going to be talking about phase in group velocities. Okay, so if we consider a single sinusoidal wave that has lived forever, okay, so that would be y xt is equal to the amplitude times the sine of kx minus omega t, right? And then plus some phase factor, okay? Now, remember what I said, this is going to be a single sinusoidal wave that has lived forever. Now, I don't think we understand the ramifications of that yet, right? But you will as this chapter unfolds. So if this wave, right, had not lived forever, then I couldn't write it as a single sine or cosine function. Okay, it would be some superposition of sinusoidal waves. Okay, but in order to be a single pure frequency, pure wavelength sinusoidal wave, it must have lived forever or is living forever. Okay. So just some language here as this unfolds, right? So this whole argument here is sometimes called the phase. This factor here is called the phase factor. Okay, and the phase factor just allows you to change the initial time that you begin to watch this wave evolve. Your starting point when you start observing it. For instance, if phi were equal to pi over 2, then y of xt would be equal to a cosine of kx minus omega t. Okay, so there's nothing magical about sines or cosines. We can interchange discussions between them. As a matter of fact, I like cosine better, so let's in general let's write y as a cosine function, be cosine of kx minus omega t plus some phase factor. Okay, and so let's pretend, right? Well, let's just leave the phase factor in there, right? We don't have to, right? We don't have to take it out, right? So if we imagine, right, if we imagine that we're watching a wave, and here it is. Look, here it is at some time t. This is t. This is y of x and t. And then we take another snapshot of it at some later time, right? And so, that's gonna that might look like this, right? So it might look like this. Okay. And so if we look at points here, say this is a point here, and this is the same phase, right? So it's going to be the same. It's going to represent the same height or displacement of the medium. Then we could calculate, right? We could calculate the speed of the wave, because this is a point of constant phase, right? So these are points of constant phase. Points of constant phase, not phase factor, of constant phase, right? The argument in the parentheses of that sinusoidal function. Okay. So points that move at constant phase then. So points that move at constant phase means that if we go and look at the argument here, this kx minus omega t plus phi is equal to a constant. Okay. And let me just rearrange this a little bit. I'm going to make this kx is equal to omega t plus phi plus the constant that the phase is equal to. And I can divide through by k. So x is going to be equal to omega over kt plus phi over k plus some constant over k. Now we have to remember what k and omega are, right? So, so omega is the angular frequency. It's in units of radians per second. And for a particular sinusoidal wave, that's equal to a constant, right? So we know that omega is equal to 2 pi times the frequency. So for a particular wave like this, right, this wave is at some constant frequency. And wavelength. Okay. So K, you will remember, is called the wave number. And the wave number then, K, is going to be 2 pi over lambda. And so that has units now of inverse meters. Okay. And remember from our statement above, these are constants. These are constants, again, for our sinusoidal wave that is living forever, all right? So if we want to find the velocity, we know that the velocity by definition is the change in x with respect to t. And so we can do that up here, right? So the velocity is going to be dx dt, which is going to be omega over k, right? Plus the derivative of a constant and the derivative of a constant. And so that's going to be 0. And so we give this a name. We call this the phase velocity. You might see Vp for phase. Some books might write it as V of phi, again, to talk about phase, And so that's going to be equal to omega over k. And that makes sense if we think about this, right? Because omega over k is going to be 2 pi times f over 2 pi over lambda. The 2 pi's will cancel. That gives us lambda times f, which we know is the speed of propagation of that wave. In this particular case, we're calling it the phase velocity. Okay, so this is the phase velocity. And it's exactly what it says, right? It's the velocity of the phase, okay? The velocity of the phase. All right, so that's that piece. And we've seen it before, but we didn't call it the phase velocity. We just called it the velocity of the wave disturbance, okay? So now I want you to think about the following, the following idea, all right? So, and I'm going to write this out. So a single sinusoidal wave is not good. As a matter of fact, it's insufficient, right? It's so not good that it's insufficient for sending, right? For sending information. Okay. So the reason for this is the wave is unchanging. The wave is unchanging throughout time and space. As a matter of fact, if you imagine you have a sinusoidal wave detector and you are detecting this wave, you will detect the same wavelength and the same frequency and the same amplitude forever. So it really is not conveying any information to you, okay? Other than its wavelength, frequency, and amplitude, which is the same all the time, right? So it's not changing at all, okay? So something must change. In order to send information, something must change. And we say sometimes that it is modulated, right? That something is modulated, right? And what could be modulated? The frequency, right? The frequency could be modulated, or the amplitude could be modulated. And in a more complicated sense, the phase could be modulated, okay? Right? So something must change, such as the frequency or amplitude, in order to transmit intelligence. And if you think about radio, right? So just as an aside here, if you think about radio, typical radio has two bands, right? It has an AM band and it has an FM band. And that AM band, the AM stands for amplitude modulation. And the FM band stands for frequency modulation. And I'm not going to go into the details of how an AM and FM radio work. For those who are interested, you can certainly look it up. AM radio is, of the two, the easier to understand. And I urge you to look up AM radio and to read a little bit about it. It was the first type of radio that was invented, and by modulating the amplitude, intelligence can be transmitted. Okay, that is, information can be transmitted. Okay, beautiful. So now let's introduce these notions, right? In terms of well, not in terms of particles, right? We don't have to do it quite yet, right? But let's do the following example, right? So let's look, right? So let's look at the superposition of two sinusoidal, sometimes called harmonic. Whenever we use the word harmonic, where we are referring to sinusoids. So harmonic, to sinusoidal or harmonic waves that are very close in frequency. Okay, as a matter of fact, I'm going to say very close in angular frequency, since that's going to be easier to work with. Right, so they're going to be very close in angular frequency. That is, omega 1 is going to be approximately equal to omega 2. And we're going to mandate that they have the same amplitude. It'll just make the arithmetic easier. Okay. So the composite wave then is going to be y. It's a function of x and t. It's going to be a cosine of k1x minus omega 1t. We're going to suppress the phase factors here, okay? Let them be equal to, both be equal to 0. And then this will be plus a cosine of k2x minus omega 2t. Phase factors now are going to be equal to 0. Okay. Now, we'll need a trig identity. And this is not one that you typically remember. And so it can be a lookup. Just look up on Wikipedia trigonometric identities. Cosine of theta plus or minus cosine of phi is going to be equal to 2 cosine of theta plus phi over 2 times the cosine of theta minus or plus phi over 2. Okay. And so then what we get then is we get y as a function of x and t. It's going to be 2 times a. It's going to be the cosine of omega 1t minus Don't know why I wrote it that way, but it doesn't really matter. Let me just erase this. Okay, and let me just pause here just 1 second. Okay, I'm back. So this is going to be then K2, K2, K2x minus omega 2t. And then this is going to be then minus let's do it this way. So this will be, we'll do the plus piece first, right? So it's going to be then plus K1x minus omega 1t, and that's over 2, right? And then that's going to be times the cosine of 1/2. That's going to be K2x minus omega 2t minus K1x plus omega 1t after distributing in the negative sign. Okay. And so then this is going to become then 2a cosine of 1/2. This then will be K2 plus K1 x minus omega 2 plus omega 1 t, okay, times the cosine of 1/2 is going to be K2 minus K1 x, and that's going to be then minus omega 2 minus omega 1 t. Okay, beautiful. All right. So now what does this look like, right? So so this, if you actually were to plot this up, okay, then what you would have is the following, right? You would have, this is then this is going to be x. This would be y, and then you would have you'd have what is called the broad envelope, right? This is the envelope. And this is going to be 2a cosine of delta k over 2 times x. Okay, so this then is going to be delta k. And again, this is going to be at some, we can let this be at some time, right? T equals 0. So this is a snapshot at t equals 0. And then under, in this envelope, you have a high frequency component, right? And that's going to be the cosine. It's going to be then cosine of k1 plus k2 over 2 times x, right? That's going to be this piece, okay? All right, so here you're going to have a low frequency component, this broad envelope, and you're going to have a high frequency component. So this piece, let's change up colors here. So this piece is going to look like the cosine of 1/2. This is going to be then, this will be k2 minus k1x, right? Minus 1/2 omega 2 minus omega 1 t, all right? And so I can write this now as cosine. This will be delta k x over 2 minus delta omega t over 2. All right. So going back to our nomenclature, right? If we were to look at 2 points on this envelope, right? So these are 2 points of constant phase, right? These are 2 points of constant phase. Right, so that would be, that's this, all right? So we don't call this now the phase velocity. So the velocity of the envelope, okay? So, right, the velocity of the envelope we call the group velocity. And so if we now look at that, okay, same way we did before, this is going to be delta k x over 2 minus delta omega over 2 times t is equal to some constant, right? These red dots up on this curve. And again, rearranging this, right? So this is going to be x over 2 is going to be equal to delta omega t over 2 over delta k, right, plus constant over delta k. I can multiply through by 2, so x is going to be equal then to delta omega or delta k times t plus 2 times a constant over delta k. And so now if we were to take the velocity of that envelope profile, that's now not going to be omega over k. It's going to be delta omega over delta k. And we call that the group velocity. And so clearly, right, that's going to be a different velocity than the phase velocity, right? And so if we had, right, if we had a superposition of a continuous set of sinusoidal waves, then the group velocity would be then d omega dk. Okay, so this would be the group velocity. All right. So this mirrors pretty much the development in the textbook. So it's important that we get terminology down. And again, if you need to go back and review, then Halliday, Resnick, and Walker, right? Waves 1 is a good review for this. Again, looking at the superposition of two waves gives us a broad envelope, right? Which again, because of the difference between this being small, right? Then we know that the wavelength is going to be large. And so there's the wavelength that's very large, because remember, K is proportional to 1 over lambda. Okay, so if this is small, then this is going to be large. Okay, so that's the broad envelope of a very large wavelength. Underneath that envelope, we have a sum of two Ks. And again, here, if K is large, right, K large, then since that's proportional to 1 over lambda, then lambda is going to be small. Okay, beautiful. All right, so let's end there. Okay, and this is not easy stuff to wrap your head around. You might need to go through this lecture a number of times, read the textbook, and when we get back, we'll begin to segue these ideas to particles, because from the de Broglie hypothesis, right, particles now act like waves. And from that, we're gonna have a conundrum. And so we're going to solve that conundrum using some of the ideas that we just developed here. Okay. All right. Very good, guys. We'll stop there and pick up a little bit later. Bye.